Hi, we're going to look at an example here where we're asked to evaluate a triple integral over a region, and this is one that works well with spherical coordinates. So we'll also talk a little bit about how you would know that spherical coordinates is a good choice. So we always want to start with a picture of the region. This is just the first octant portion of the region inside the sphere. So one important thing to remember when you're doing triple integrals is that you're evaluating that integral over a solid region. So it's not just the surface of whatever region you're working on, but it's that solid region. So this is not just the surface of the sphere, but if I'm doing a triple integral, the only way for that to be defined would be if it's this solid closed and bounded region. So this would also include the coordinate planes x equals 0, y equals 0, and z equals 0 behind that surface. All right, so this one works well because this solid in spherical coordinates has boundaries that are all constants in spherical coordinates. So if we think about theta as like that hinged door that's hinged on the z-axis and rotates from the positive xz plane toward the positive yz plane, then you see that in the xz plane, let me label my axes here, in the xz plane, that's where you would have theta equals 0, and then as you rotate through that region in the direction of increasing theta, you get here to the yz plane, and that's where you'd have theta equals pi over 2. So you've rotated through that 90-degree rotation. And then for phi, remember that phi starts on the positive z-axis and rotates downwards. So as you go through that region in the direction of increasing phi, you would start at phi equals 0 on the positive z-axis, and then you would leave the region when you get to the xy plane, which would be when phi equals pi over 2. And then for rho, remember rho is a radius from the origin, so we'd start at rho equals 0, which is at the origin. That corner at the back of my solid region here would be where rho equals 0, and then you come outward in all directions, and then you would exit this solid when you get to the surface of the sphere, which would be at rho equals 2. So this would be a region that's great in spherical coordinates. This is really like a box. In rectangular coordinates, the equivalent of that would be a part of a sphere or cones in spherical coordinates. So that's how you might recognize that this problem works best in spherical coordinates. It's really about the region, and that region works nicely in spherical coordinates. All right, so when I set up this integral, I also need to remember that I'm going to have to convert the function to spherical coordinates. So I need to remember my conversion formulas. So we talked about that you are supposed to know those. So y equals rho sine phi sine theta. We also have one for x, which we're not going to need for this problem, and one for z also. The other one we're going to need to remember is what the dv is in spherical coordinates. So rho squared sine phi d rho d phi d theta, and those differentials at the end can be in whatever order is appropriate, but the big deal there is that you remember you have that extra rho squared sine phi, which comes from the geometry of that partition in spherical coordinates. Okay, so let's go ahead and convert this to spherical coordinates and set up our limits of integration, and then we'll evaluate the integral. Alright, so the y function that I'm dealing with in my original integral, need to convert that. So in place of y, I'll write down what that is. And then my dv, I need to remember for my dv, I get this extra rho squared sine phi. And then my differentials, d rho, d phi, d theta, I can put in whatever order is appropriate. For this one, it does not matter at all what order you do them in, because all of my limits of integration are constant. So I'm just going to do them in that order, rho, phi, theta. And let me set up my limits of integration here. So rho will go from 0 to 2. Phi will go from 0 to pi over 2. And theta will also be from 0 to pi over 2. So there's the integral set up. Next step would be to simplify what I'm going to integrate. Remember that you also have to integrate this rho squared sine phi, so just simplifying that with your y squared expression before you start doing integration. Alright, so be careful. I've got several different sine functions here, and some of them are sine of phi, and some of them are sine of theta, so just making sure you kind of keep track of that so that you have those things kept straight when you're ready to do your integration. All right, but I'm going to integrate first with respect to rho. And so there's what I get when I integrate with respect to rho, and then I just need to plug in my limits of integration for rho. Okay, so there's what I get after I plug in 2 for rho and 0 for rho and subtract them. So let me go ahead and scroll up here so we have some space to finish the integration. So the next thing would be to integrate sine cubed of phi. So I'm going to separate that sine cubed of phi. I'm going to do a little scratch work here into sine of phi times sine squared of phi, and then use Pythagorean identity to rewrite the sine squared of phi in terms of cosine. Alright, so there's what I get, and again I'm just really leveraging what I've learned in Calc 2 probably for integrating powers of trig functions. So then I would do a u substitution, u equals cosine phi. My du is a negative sine phi d phi, so I need to make sure I keep track of that negative. I actually often do these u substitutions in my head without actually substituting in, but I usually do write down my u over here to the side so that if there's any extra stuff to keep track of, it kind of helps me remember to keep track of that. But I don't actually often write out the u substitution over here. You're welcome to do that, or maybe do some scratch work for that. But the issue with doing that is that inside that double integral, rather than kind of doing it in your head, is then you have to be a little bit careful about your limits of integration. So that's why I prefer to really just kind of do the u substitution in my head, or maybe some scratch work for that. Okay, so here I wrote down what I got after I did that u substitution, just so you can kind of make sure you're keeping track of everything. So this minus sign out front is from the extra negative that I get in my du for my sine phi d phi is replaced by negative du. And then when I integrated my 1 minus u squared here with respect to u, I got u, and then I substituted u equals cosine phi, minus 1/3 u cubed, and then I made my substitution back into that u equals cosine phi. So there's what I get when I've integrated, after I did that u substitution, integrated with respect to phi. I now need to plug in my limits of integration and simplify that. Okay, so after I plugged in my pi over 2 and my 0, here's what I get. I did go ahead and distribute my minus sign through, so that's why my signs here on those two terms are different. And then I plugged in my pi over 2, and then I plugged in my 0, and I'm subtracting them. One trouble spot that I see a lot of students have is that they try to keep track of doing a u substitution, any extra negatives for that, plugging in limits of integration, and evaluating trig functions, and then remembering to subtract all at the same time, and then they often mess up something. So I tend to write out a little bit more here than I do on some other things, because I know I would mess that up if I didn't. Alright, a whole bunch of this stuff simplifies though, so let's go ahead and evaluate the trig functions and simplify. Alright, after I do that simplification, so cosine of pi over 2 is 0, so all of that part just zeroes out. I need to make sure I don't forget my minus sign here. And then cosine of 0 is 1, so in this last set of trig functions here I get negative 1 plus 1/3. So when I combine those I get negative 2/3, and then times the negative 1 out front. All of this simplifies to just be 2/3. So I can take that 2/3 times my 32/5. I'm going to go ahead and pull that all the way outside of the integral, and then I'll be ready to integrate my sine squared of theta. Alright, so we're going to be ready to integrate this sine squared of theta. I'm going to go ahead and scroll up here so we can do that. To do that you need to remember trig identity. So I'm going to make that substitution and then do that integration. Alright, so for this last step, you're almost to the end here, but you do have to be a little bit careful on this last step. When you do this last step, I'm going to go ahead and pull the 1/2 out front and simplify that with my 64/15. And then when I integrate with respect to theta, this first part's easy, I just get theta. The second part, there's technically another little u substitution there that you have to be careful about, and you might do that u substitution in your head, that's fine, but you have to remember you get an extra 1/2 from that, but that's really just for this term where you have the cosine 2 theta that you're integrating. Alright, so here's what I get after I do that. So notice I have this extra 1/2 just on the integration term from the cosine 2 theta. Alright, so one last step, plug in my limits of integration, tidy it all up, and then we'll be done. Alright, so when I plug that in, here's what I get. A whole bunch of stuff here drops out and becomes 0. So I'm left with 32/15 times pi over 2, which simplifies to 16 pi over 15. So that is the total sum of that function y squared on that solid region that we started with here at the beginning. So that first octant region enclosed by the sphere x squared plus y squared equals 4, and then to make it a solid region we also have to include those coordinate planes.